All right, I'm Sam Finkley with DHEC's Office of Public Health Preparedness. I started my career at DHEC in the Bureau of Radiological Health in the late 70s and went through all of the changes and improvements to the emergency response plans that Mr. Williamson has described to us after 3 Mile Island. I took a brief detour of about 20 years to practice environmental law, and since 2005 I've been back in the emergency planning business. And what I want to talk to you today about is an initiative that DHEC has undertaken, partly inspired by the events of Fukushima and partly inspired by one of the national planning scenarios, which is all states and local governments are required to have plans to deal with a number of specified scenarios, one of which is the detonation of a 10-kiloton nuclear device somewhere in your jurisdiction. And what I want to talk to you today about is what implications something like that or an event like Fukushima would have for South Carolina, and what we need to do in order to prepare for it, and what you as medical professionals can do, and what resources you can call on. And so I'm going to start from certain assumptions, and Mr. Williamson has told you about all the defenses in depth that the nuclear power plants design into their facilities and build into their facilities, and what they in the state practice to respond. But I want you to assume with me that some event has occurred that, despite their best efforts, or has escalated to something like what happened at Fukushima, or that a terrorist group has deployed either a radiological dispersal device, a dirty bomb, or has acquired somehow a nuclear device and set it off somewhere in South Carolina. And the consequences of that are, we have a large contaminated area, and it's going to be contaminated for a long time. We've got a lot of people who are displaced. We've got a lot of people who are injured and contaminated. And what I want to talk about for the next 45 minutes or so is, what are the public health consequences of that? What can you as a medical community do? And what does the state and the local governments and the community itself need to do and need to think about in order to prepare for that? This is a this is a radiological survey of the area around Fukushima, and you can see that the Fukushima is approximately there. This is going to be difficult to do. And so in each of the other plots, you see that semicircle that's whited out, and I assume that's because the radiation is going to be very difficult to do. They didn't show the radiation survey in those areas, but look at the area around. And notice the scale on this slide. That's 50 kilometers is that bar. 50 kilometers is 30 miles, and so that's roughly the distance from here to, the other side of Columbia. And see how far the plume or the contamination had extended. And also notice the different colors. And notice, for instance, in the middle row of images and the bottom, you have areas of relatively low contamination closer to the plant than the areas in the far south at higher levels. And that's an example of the difficulty that we have in trying to make accurate, immediate, short-term projections. I'd like to use this pointer, but the people who are seeing this on the rebroadcast won't be able to see it, which is why I'm trying to use the cursor. But it's not going to let me do it. Now, these survey results are the accumulation of weeks and months of measurements. And so what it shows you is the contamination that leaves the plant depends very much on the operating history of the reactor, or in the case of it, and it also depends on the meteorology and the local topography. And so the area just to the south and west of Fukushima is mountainous, and you may suspect that that's possibly why the contamination levels in those areas is lower. The wind shifted while Fukushima was actually releasing material, and so for part of the time the wind was blowing out to sea, so that was good. Then it turned around and blew to the west, and then it turned and blew to the north, and so people who had evacuated out of the areas to the west of the plant suddenly found themselves under the plume again, and they had to evacuate again. So the models can only do so much, and they're very sensitive to the detailed meteorology. And so the best we can do is to do modeling in gross and make our best estimates and take conservative responsive measures. All right, that's the release from a nuclear reactor, or two nuclear reactors in this case. Here's an example of the kind of effects that you would expect from a 10 kiloton device detonated at ground level. And here again, the precise details are going to be very sensitive to where the device is located, what the local topography is, what the detailed weather is. But notice the scale, and so you expect a lot of blast damage in close being 3 to 4 miles in this case. And so, but the fallout zone, or the area where dangerous fallout can be expected, is going to extend much further out, and it's also going to be sensitive to the meteorology at the time. So imagine, if you will, that superimpose this in your mind on downtown Charleston. Assume that one of the containers in the State Ports Authority shipyard or port has exploded. 3 miles from there is to the other side, is to Mount Pleasant in one direction and the Citadel in the other direction. The plume is going to extend all the way up the Charleston Neck, and so everybody who's in that zone is injured and potentially contaminated. Well, I misspoke. The people in the fallout zone are not necessarily injured, but they are definitely potentially exposed and contaminated. Now, one of the reasons I'm telling you this is because here's a map of South Carolina that shows where each of the operating commercial reactors is. And there's also one about there in North Carolina that is a factor for some of our eastern counties. And there's one north of Charlotte that I didn't show on here. And we've got very good plans in the counties immediately around those 5 locations. And we practice there, we do the annual drills that Mr. Williamson described to you around those 5 locations. But notice where we don't have any nuclear plants along the coast. And so we don't have the same level of preparation and planning along the coast that we have around some of the other plants. We also, Spartanburg, the I-85 metropolitan complex extends through the Oconee planning zone, but it also extends outward. So we have a number of areas in the state where we don't have the level of preparation that we have immediately around these reactors. And we also, if the event that we're preparing for is a dirty bomb or a nuclear device, there's no guarantee that the terrorists are going to choose one of those 5 locations to deploy it. I'll skip over that one because Mr. Williamson has already covered that very well. This slide shows a hypothetical but reasonably realistic inventory to be expected in a reactor. This is taken from one of the NRC planning guides. And I included this primarily to show you that we undertake a lot of preparation to protect people against radioactive iodine, but that's not necessarily the only thing included in the plume that we have to protect them from. And in particular, cesium-137 is a significant part of the inventory of most hypothetical reactor releases, and it has a much longer half-life than a number of the other isotopes. So I'm going to talk about that in more detail in a little bit. Mr. Williamson has told you about the emergency plans that we have around the various reactor sites. And in addition to the plans for evacuation, we have recommendations that people shelter in place. DHEC and Clemson and FDA may have to impose controls on food crops and dairy production in the ingestion pathway. And we have plans for distribution of potassium iodide immediately around the facilities. For those of you, for those doctors that aren't part of one of these plans and are not endocrinologists, and for those of you that are just interested in how the state prepares, I want to talk a little bit in a little more detail about potassium iodide. It is a stable salt. It's chemically similar to table salt, and as a practical matter, it never goes out of date, but FDA being FDA, it does have an expiration date on it. And DHEC has just this past week swapped out its now expired inventory for a new batch of potassium iodide. The radioactive iodine is one of the constituents of a release from a nuclear reactor. It's also can be found in the fallout in the fallout from a nuclear device, although not as much and not as high proportions as it would be from a reactor. And any radioactive iodine that you inhale or ingest is going to be concentrated in your thyroid unless the thyroid is already saturated. And so the reason we distribute potassium iodide is that if a person can take it before or shortly after they are exposed to radioactive iodine, then the thyroid will already be saturated, and the radioactive iodine won't be concentrated in the thyroid. Now, some people say, well, I have Morton's table salt at home and it's iodized. It says so on the label. And that's where it's there because it's a necessary dietary supplement. The endocrinologists know what I'm talking about. But you would have to eat enough salt. You couldn't eat enough Morton's table salt in a short enough period of time to do you any good. Now, South Carolina does have high concentrations of iodine in its leaf crops, particularly along the coast. But it's not prudent for us to assume that people are going to get their necessary stable iodine from those sources either. So we distribute potassium iodide. If potassium iodide is going to work at all, it needs to be taken quickly, either before exposure or within about 4 hours after exposure. This graph shows the drop-off in efficacy with time after the exposure. Now, it does have limitations. If you think back to the slide I showed you showing all the other isotopes that would be expected in a radioactive plume, the radioactive iodines are only a fraction of the total. And so potassium iodide is not going to protect you against any of those other isotopes. It's not going to prevent the radioactive iodine from being inhaled or ingested. It's still going to be in your body, and it's still going to cause some exposure. What it does do is it blocks the thyroid, and so the iodine is not concentrated in the thyroid, and because of the nature of the radioactivity that's emitted by radioactive iodine, its effects are felt very close to the deposition location. And so if the iodine is not concentrated in the thyroid, then the exposure is diffuse over your body. It's not concentrated in the thyroid. And you've seen this slide before, but once again, I'd like to make the point that we have all these preparations in those 5 locations and in 10-mile circles around each of those plants, but we don't have that kind of preparation in place anywhere else in the state, because under most circumstances it's not needed anyplace else in the state. All right, for those of you that are radiologists or practice nuclear medicine or health physicists, now's a good time to take a cup of coffee, because this is a elementary primer on radiation and health physics. You probably remember certainly from your undergraduate days, if not from medical school, that the 3 primary types of radiation, there are others, but these are the 3 main ones. Gamma radiation is like X-rays, and if you were anywhere near, I mean, it penetrates the yards of air and soft tissue, bone. It's just like an X-ray, different energy spectrum, but it's basically an X-ray. Beta emitters, of which I-131 is an example, emit electrons. The electrons are stopped in a matter of a few centimeters, and so, or several feet of air. So if you have a pure beta source, you protect it if you can get a few feet away from it. If it's in your body, then it's going to affect the tissues within a few centimeters of the point of deposition. So that's the point. That's why we've stressed earlier that potassium iodide will prevent the radioactive iodine from being concentrated in the thyroid and depositing all its energy in the thyroid, but it won't, wherever it does end up in other parts of your body, will still be exposed. Now, alpha particles are a much smaller fraction of the expected plume inventory, and they're basically helium or ionized helium atoms, and they have very short transmission paths. They're blocked by almost anything: skin, paper, clothing. But if they are ingested into the body, they tend to concentrate in the bone and certain other organs, anything that picks up heavy metals. And so if you do inhale or ingest alpha particles, it's not good. There's a lot of confusion in this country about the units in which the radioactivity and health physics are expressed, because we and North Korea and Albania have not adopted the international system of units. We use them, but we also use our old English system. So you can hear references to curies or becquerels, which is a measure of the number of disintegrations per second. Roentgen's is a measure of the amount of radiation measured by how much ionization it causes in dry air. And then Rads, Grays, Rims, Sieverts all refer to how much radiation is actually absorbed by the receiver. And they all measure different things. They're defined differently to the health physicist. They are not identical, but for a clinician, very roughly speaking, 1 rad, 1 rim, 1/100th of a gray, or 10 millisieverts all have approximately the same physiological effect. And so if you keep those conversions in mind, when you see some of these later slides where the units are different, it'll help you keep it in perspective. Each radioactive isotope is characterized by its mode of decay, the energy of its decay mode, and how rapidly it decays. And the measure we use is the half-life, which is the time it takes for 1/2 of the original quantity to decay. And so after 10 half-lives, you can expect that you're going to have about 1/millionth of the original inventory. That's good for something like radioactive iodine or I-131, which has an 8-day half-life. So in 3 months, you're down to 1/millionth of the original inventory. For something like cesium-137, which was, as you recall from those earlier slides, was also a significant factor in Fukushima and could be expected to be a significant factor in any similar event, has a 30-year half-life. And so now we're talking 300 years to reduce the contamination to 1/millionth of whatever level it is that you measure today. And when I get to the last part of my presentation, that's going to be a big factor. The individual response to ionizing radiation is like most physiological response. It's highly dependent on the individual. It's also dependent on the amount of exposure, the organs that are exposed, the rate of exposure, and your age. This slide shows that the infants and small children are much more sensitive to thyroid exposures, and so it's most critical that they get or be protected from exposure to radioactive iodine, preferably by evacuation, but if necessary by prompt administration of potassium iodide. The bottom of the slide, I gave you the typical thyroid ablation dose so that you can, for a point of reference. And the other point is that you notice from the bottom bar on this slide that adults are much less affected by radioactive iodine, and what the people at Oak Ridge tell me is that for our generation, you know, you take it if you want to, but it's not going to do you any good. It won't do you any harm, but it won't do you any good either. And if for no other reason that any effect it has is not going to show up until you're dead for other reasons. And I'm not going to go over the slide in great detail. You can study it at your leisure. But it gives you a comparison of various exposures and what physiological or health effect can be expected to somebody exposed at those levels. And you see that there's considerable range in the exposures from half a rem, which you're allowed to, which a holder of a radioactive materials license is allowed to allow members of the public to be exposed to the mid-range of 25 to a couple of hundred rem, which do have health effects, but they're difficult to identify in an individual. At around 25 rem, if you have royals enough in time and are really interested, you can do detailed cellular studies and see the chromosomatic effects due to radiation, but it's very difficult to find an acute effect. When you start talking exposures of several hundred rem, then you will see some health effects, typically nausea and vomiting. Yes, Dr. Ball.
Yes. Sam, the average adult in this country is exposed every day to radiation, sunlight, computers, televisions. What order of magnitude on this scale? Is it around 0.1 to 0.5 rem?
The question was, what is the average person, how much radiation is the average person exposed to in the course of daily life? And the answer is, in South Carolina, in particular in the Midlands, we get about 1/10 of a rem, 100 millirem per year. Now that's also depends on where you live and where you work and how much you travel, how much you fly, and whether you live with somebody. So you get 100 millirem just from walking around downtown Columbia. If you go to the State House, you get more because the Winnsburg granite, which it's built of, is loaded with uranium and thorium. The sand around here has got thorium in it. You go to higher elevations. If you go to Denver, you can expect to pick up another 100 millirem a year. If you fly coast to coast, you get about 4 millirem per trip. If you have granite countertops in your kitchen, you get about 4 millirem a year. If you live with somebody, you get about 4 millirem a year because the other person's got radioactive potassium in their body. One other point that I would like to make about this slide is I've included the references here, and if you go to this www.bt.cdc.gov, and I'm going to refer to that site several other times, it's got a number of references applicable to this topic and a number of references that are specifically targeted to clinicians, including just-in-time training that's available online. And so I recommend that to you for your further study. This is a continuation of the previous slide and shows you that at some levels of exposure you may see some erythema. At doses of anywhere to 1,500 to 4,000 rads, you can start to expect to see permanent skin damage. But you won't see that immediately in the ER. That's going to take weeks to months to manifest itself. All right, from the clinician's perspective, from the ER perspective, somebody who's gotten a high dose over a short period of time is going to present with nausea, vomiting, changes to the blood tissues, and other observable effects, but you may also find that the worried well or people who have been exposed but at lower levels are going to exhibit those same symptoms, the nausea and vomiting, pallor, as psychosomatic symptoms. If you are presented with a patient that's received doses above regulatory limits but less than the ones where you expect to see the acute physiological immediate effects, you may be able to measure that and monitor it if you've got the time and the resources to do so, but you're not going to be able to do anything for that person in the short term in the ER other than to give them some reassurance. Ever since the Japanese bombings, there have been detailed studies of the populations that were exposed in Hiroshima and Nagasaki. Since then, there are ongoing studies of the populations that were exposed around Chernobyl, and Dr. Tim Musso at the University of South Carolina here and others have started doing long-term monitoring of the populations around Fukushima. And so we've got roughly 60 years worth of experience of people who were exposed to various types of radiation at various levels. And what has been found is that there are measurable effects from radiation exposure, but the statistical significance is low enough so that it's difficult to say, or it's impossible to say that any one person will or will not have an adverse response to radiation exposure. This chart shows the excess light the best estimates of the excess lifetime risk of a fatal cancer from short-term radiation exposure, but bear in mind that almost all of the radiogenic cancers are clinically indistinguishable from a spontaneous cancer of the same type from any other source. Now, if you think back to the chart that showed that compared the regulatory limits to the limits at which you could expect to see physiological effects, the plant workers and occupationally exposed workers are allowed to, by law, to receive up to 5 rem a year. At 10 rem, then the estimates are that approximately 1 excess cancer out of 42 would be due to that 10 rem exposure. If you go to the cdc.bt.gov site and look at some of those, the just-in-time training and the recommendations, you'll see that they make the same point that our colleague addressed earlier in his comment, that the Army's trained to treat the physical injury first and deal with the contamination later. And CDC and FEMA and NRC are all making the same recommendation. But that has consequences, and I'm going to talk about that in a minute. Slightly exposed patients, and you may not know who those are if they are not contaminated, are going to need psychological support, but you're not going to be able to detect any health consequences in them. Somebody who's been exposed at levels of hundreds or thousands of rad is going to be expectant, but patients in between that are showing the acute radiation syndrome can be treated, but it's highly resource intensive. All right, now having gone through all that background, I'd like to talk about what DHEC has started to take out to the population, to the community as a whole, and why I'm talking to you today. Our assumption is that if we have to respond to one of the events that I hypothesized early on, we're going to, first of all, it's a low probability but high consequence event. We have only 3 or 4 examples well, we only have 2 examples of a Fukushima-like event, Chernobyl and Fukushima. We have 2 examples of a detonation of a nuclear device, Hiroshima and Nagasaki. And so we hope and we expect from the intelligence summaries that our future experience will be similar. And so my point is, these are low probability events, and we DHEC have decided that we don't think it's a useful use of our time and resources to try to come up with detailed plans for responding to them comparable to the detailed plans that we have for dealing with hurricanes or with responding to fixed nuclear facility accidents, because we're required by law to practice those every year. And so we've concluded that if we try to do that level of detailed planning, then it would be a full-time job and then some to keep it up to date, and it would still be out of date when we actually had to use it. So what we're proposing is that we engage in a mutual dialogue. We've drafted up what we're calling a framework, and DHEC has started drafting a plan to respond during the first 72 hours, or at least from a DHEC perspective. But going beyond that, we think it's necessary to have wide-ranging discussions with a variety of communities around the state. And I want to give you some examples as to why. I'm going to run through a series of excerpts from Japanese news stories. The first one makes the point that we've talked about, and that is, if you think back to the slide showing the distribution of radiation around Fukushima, and look at the isotopes that are involved, and think about what I said about the implications of the half-life of radioactive isotopes, those areas they are contaminated now at levels above the Japanese regulatory limits for continuous occupation, and they're going to be contaminated for years. Now the use of that word, likely to remain uninhabitable for decades, implies that just because those areas are contaminated, people aren't going to move back into them. Well, assuming that it's so, and it's not so, how would we as a state and a community deal with having to abandon the Charleston Neck for years, just to pick an example? The Japanese have found that the doctors and nurses in some of the facilities that haven't been abandoned have quit and moved elsewhere. They found that they've got these populations that were displaced, put in shelters, required to stay there for months, and they got increased mortality in those populations, not due to the radiation, just due to the evacuation. And we know that's so. We know that an evacuation has costs, and that's one of the reasons evacuation is undertaken very carefully. Our supposition in all evacuations we practice in South Carolina, and we've done a number of them, is that you'll be able to go back into your house as soon as the water's gone down and the wind's stopped. Well, I'll tell you a personal anecdote. My cousin Wendy and her husband heard that a hurricane was headed their way and that people were that evacuation was being recommended. So Wendy said, well, let's just close up the restaurant and head out for the weekend, and we'll come back on Monday. And so they packed a dog, 2 cats, a change of clothes in the car, and on Saturday night, August the 26th, 2005, they headed for Vicksburg. Well, Mark went back to New Orleans about 7 months later to sell the restaurant, to clean all the, to throw away all the food that had gone bad and sell the restaurant. Wendy's never been back. So if we had to think about how we would respond and what the implications would be if we have that kind of displacement in South Carolina. The Japanese are giving us some examples of what happens. Healthcare delivery has been compromised. Not only have some of the doctors and nurses gone elsewhere, some of the facilities aren't available, and people have lost their medical homes. Now, a few minutes ago, I commented on that, the quotation that said the areas remain uninhabitable. And the implication was they're uninhabitable because the radiation exposure at those levels of contamination are above regulatory limits, and so nobody would go back in there. Well, people are going back in there. And they are not necessarily waiting for an approved government cleanup. They're going in and taking matters into their own hands. And you're dealing with contamination that can't be seen or tasted or smelled, and so you either have a survey instrument or you just assume that if you sweep up all the dirt, then you'll remove the contamination. So one of the things that they're doing is they're getting their own survey instruments. It's predictable that if we had an event like that here in South Carolina, within 12 hours, you would see Screaming Billy or his clone advertising potassium iodide and radiation survey instruments on TV. And without knowing what type of instrument you're getting or where it came from or whether it's been calibrated or anything else, its readings may be useful, may not. You as a civilian have no way of knowing. The Japanese made a number of what we now see in retrospect were missteps in responding to this Fukushima accident. The utility dropped the ball on what information it was giving to the government. The government dropped its ball on what information it was giving to the public. And even after the fact, where they're trying to recover areas, they made some surveys which now appear to be superficial and overly optimistic. And so the Japanese individuals are making their own measurements, and they've found enough instances like this one so that the government's basically having to go back and resurvey everything. This is another example of what we already know, and that is the psychological effects in an incident like this are going to be far more significant than most of the health effects. There have been several national level exercises that give us some guidance in how we should move forward on this. Liberty RADx was an exercise that hypothesized a dirty bomb in Philadelphia, and they brought in a number of state and local representatives and people from the federal government, and they used I think Los Alamos did the modeling for them, and so when they started doing tabletop talks about what it would take to monitor the area that was contaminated and clear it to levels down to regulatory limits, EPA concluded that EPA didn't have enough staff in the country to do continuous long-term monitoring at that level. So coming back to the framework that we're starting to discuss, we've made a number of assumptions. First, that a response is going to require cooperation from everybody. The government's is not going to have the resources to do everything for everybody, and frankly, we probably shouldn't be expected to, because these are very infrequent events. It's hard to imagine how you could stockpile enough equipment and keep it operable to provide for every jurisdiction to have all the resources it needed to do the monitoring. We don't have enough professional staff to do all this monitoring, and we're going to need to rely on volunteers and trained individuals. You know, if something like this happened today, then I would be calling for every high school physics teacher, every nuclear medicine department, anybody that had ever used a survey meter to be called to do the monitoring. And if you think about the numbers of people involved, the power plants typically plan to evacuate a few hundreds to a few thousand people from their emergency planning zones, and plan to do it in an orderly fashion and with advance notice. And so we set up reception centers outside the evacuation zones, and the plans call for people to line up in an orderly fashion and stand there patiently while each person presents to the monitoring point, to the survey point, and is subjected to a 3 to 5 minute survey. Well, you think about, Dr. Ball and I are going to Spoleto tomorrow, so if the bomb goes off tomorrow downtown Charleston, and we and everybody else in downtown Charleston starts heading up I-26, do you think we're going to line up patiently and wait there for each one of us to be surveyed one by one, 3 to 5 minutes? I don't think so. Another assumption we make, and this is where this really starts to deviate from your traditional top-down command-driven emergency response plan, is we believe that participation by everybody involved, by all communities, by state, local governments, by federal governments, by faith-based groups, the business groups, the healthcare community, needs to be prepared to make some consensus decisions on a number of topics. We've seen that the Japanese citizens are moving back into areas which, if a facility tried to get regulatory approval to allow them to remain there, would be denied because the contamination is above regulatory limits. But people don't care. They're displaced from their homes. They're going back in. And what we as a government can do is we can give them information by which they can make informed decisions about those kinds of things. We can tell them what we know based on all the information that we gather, and as I've tried to emphasize, the government alone is not going to be able to gather all the information. We're going to have to rely on information from the citizens and other groups. We're going to have to arrive at consensus decisions about cleanup standards and cleanup priorities, because we're not going to be able to clean up everything down to pre-incident levels. I mean, the Japanese are trying it in some places, but they're left with bedrock. I don't think that it's reasonable to expect that if I or some committee of people like me at DHEC or some committee of people like me at the State Emergency Management Division decided without community input that we're going to clean up this facility or that block first, then everybody else is going to be screaming about it. The only way that this is going to work in a meaningful fashion is for us to have some framework to lay out the issues, get everybody's input into the priorities, and come up with a path forward. It's going to take years. We're going to have to monitor the population for years, and the earlier we can set that up and get it started, the better off we're all going to be. Everybody's got a part to play in it, and I keep emphasizing this is not a command-driven plan that we're talking about. And we are now engaged in the pre-event planning. So I've been taking this message out to, I started taking it out to other people in DHEC. I think 4 of you have heard this, 4 times already now? I'm starting to take it out to the community groups. I'll go out to anybody, feed me lunch, and I'll tell you my horror story. And we need to get the people outside government involved. Ultimately, we need to be talking to the community groups. And we also have got a good bit of education to do. Now, I've said a couple of times that, and I'm sorry, I didn't get your name, but anyway, our Army doctor colleague said, treat the patient first, deal with the contamination later. And that is a good principle, but the person who's doing the treating needs to understand the issue, needs to understand the risk that that patient presents to him or her, the healthcare provider, because otherwise the healthcare provider is not going to be effective. If the healthcare provider is apprehensive and the support staff in the ER is apprehensive, or in the reception center or the field station or wherever, they're not going to be effective. We need to have this kind of discussion beforehand so that when people can think about it in calm, rational fashion instead of the reaction that you would otherwise get if you have the event, you have the stress of the response, and you have the fear of radiation. We need to start educating the public about the possibility that one of the recommendations that they may get in the aftermath of an event like this is to shelter in place rather than to evacuate. To the extent that people have thought about this, to any extent, the civilians, I mean the citizens, they assume that the direction they're going to get is to evacuate and that they should do so immediately. The current thinking is that based on the fallout plume inventories and the speed at which it would travel, you'd actually save more lives if people could be convinced to go inside, preferably into a building like this one, so that you're several floors below the roof and can get away from the windows and stay there for 24 hours. You'll receive significantly life-threatening, significant reduction in exposure, to the extent that the reduction is so great that you'd save 2/3 of the population that you'd lose otherwise. But that's counterintuitive. And so we need to have that discussion with people while I can think about it rationally. We need to have pre-planned communication networks and pre-planned messages so that we can get that kind of word out to people where and when it's needed and do it quickly. We need to think about using non-traditional communication methods. And we assume that at least some of our pre-planned formal communication methods will continue to work. Some may not. We'll have to use workarounds. Another thing we have to recognize is that in this era, 90% of the information people are going to get are going to be just like that. They're going to be looking at their iPhones. They're going to be tweeting each other. They're going to be holding their phones up and beaming pictures of what they see to everybody they know. And we're not going to stop them from doing that. We need to recognize it and be prepared to first deal with the information or the misinformation that flows that way, and also to use that to our advantage. This slide shows or summarizes some of the lessons that I think we should draw from Fukushima. Government's role and responsibility in a situation like this is to be as transparent and forthcoming as possible, give people information, and recognizing that it may turn out to, the preliminary information may turn out to be wrong and have to be amended. You just have to convince people that you will tell them the best you know as you know it, and we need to be able to provide the just-in-time training. I recommend looking at that CDC site for clinicians. Need to recognize that the radiological surveys are going to be long-term, so once we start this, we're in it for the long haul. And we should not rely solely on the fact that we've got regulatory limits, because they're going to be impractical, and if that's our only response, then they're likely to be ignored. As far as healthcare facilities are concerned, we have to recognize that if we're dealing with thousands of affected patients, then we as a state don't have the hospital surge capacity to deal with it in the traditional way. All the surrounding hospitals are going to have to be prepared to take in patients, some of whom will come traditional medical transport, some of whom will self-refer, not all of whom will be contaminated or exposed or injured, but you're still going to have to deal with them. They will not have lined up in orderly fashion to be surveyed and decontaminated and resurveyed before they show up in your ER. They're going to show up, and you need to be prepared to deal with them. Your staff needs to recognize that and be prepared to deal with them. And as far as medical staff is concerned, Deborah Derrick is going to talk to you about the medical, the ESAR-VIP, the medical volunteers, and she'll tell you in detail what we are trying to do about that and what some of the issues are. This slide shows some of the things that we're planned to be talking about and the issues that I've just summarized over the last 45 minutes or so for you. And these are some of the questions that I think the healthcare providers and particularly the hospital administration and the state and local governments need to be dealing with. What are we going to do if we have large numbers of contaminated people? How do we set priorities for decontaminating and recovering critical facilities? I've already said that. If we lose a major metropolitan area, we've lost all of the healthcare capacity in that area. How are we going to compensate for that? How do we accommodate displaced medical professionals? And how do we incorporate volunteers? Any questions?